Problem number 5, example 2.6. Calculate the bending stresses in the concrete and reinforcing steel using the transformed area method, where Fc prime is 3000 psi, N or modular ratio is 9, and M or bending moment is 250 foot-kip. First, we have to account for the given data based on this figure. So first we have BF, or the width of the flange. This is 60 inches right here. Then the width of the web is 12 inches here. Then height of the flange, this is 5 inches right here. D is the effective depth, or the distance from the outermost compression fiber to the centroid of the steel. That will be 28. Fc prime is 3000, we have here. Modular ratio is 9. Diameter of bar, we have number 8. And for number 8 rebars, that will be 8, and always divide it by 8. So therefore, that will be 1.0 inch. So diameter of your rebar number 8 is 1 inch. Exactly 1 inch. And there are 6 pieces here. 6 pieces. And for the AS, you can compute using the area for the circle, and diameter is 1 inch, and then multiply it by 6. So let me just have the formula. That will be pi times diameter, which is here your dB, squared over 4, times the number of pieces, which is here 6 pieces. You will have an area of steel of 4.71, and then moment is 250 foot-kip. Solution. The first step is to solve for the location of the neutral axis by taking moment of areas about the neutral axis. So we have 2 areas here, concrete and steel. But since the concrete has somehow an irregular shape, then we can have several areas for concrete. So let's assume that the neutral axis is located somewhere here. This will be your neutral axis. Alright, here. So I will divide my concrete area into 2. First, this area here. Let me shade it. I will call this first, let me just have this flange here. The combined area of the 2, I will call this one area 1, as well as on the other side. And then area 2 is the shaded area. And area 3 is the AS. Here we have area 3. So in here, for area 1, let us account for all the data in the table. Let me use a tabulated solution using Microsoft Excel. Now, in your solution, if you use a calculator, you can also use the shift solve function. It will generate the same result, because we have one variable, one unknown here, which is x, and we have to equate the moment of areas. So let's account for the areas now. Let's fill out this table. For the B of area 1, that will be 60 minus this dimension here, which is 12 inches. So 60 minus 12. And for the H, or the height, this is simply equal to the height of the flange, which is 5. Then for the area, multiply the 2. And for the y distance from the centroid of this individual area to the neutral axis. Now, let me designate this one. The distance from the neutral axis to the topmost portion or the compression fiber. Call this one x, and this is your unknown. So here, that will be x minus 5 over 2. So, equals x minus 5, or height of the flange, over 2. This is just a temporary value because we don't have the value of x yet. Then for a barred y, we have a times this one, ay. Next, for area 2, we have this area. The width is 12 inches. And the height, we don't know yet because this is still an unknown x. So, we refer to this cell. Then for the area, we drag this formula down. And this will multiply the 2. Then for the y is simply equal to x over 2 because the centroid is located here. So, x over 2. So, this value over 2. And for ay, you can drag this formula. So, that will be the product of these two cells here. And lastly, for A3, this is now the area of your steel. And we don't have B and H because the area is circular. And besides, we don't use it in our stiffness in the next table. So it is assumed to have 0 stiffness. So you don't even have to measure the dimensions. Area is 4.71. Let me refer to that cell. But you have to multiply it with the modular ratio. That is always the case if you are trying to account for area of steel as compared to the area of concrete. For the y, this is your y. And that will be D, since this is your D, or effective depth, that will be D minus X. Or since we are given D here, that will be 28 minus X. So let me refer to this. D minus X. And then drag this formula down so you can account for the AY. Now, for this particular problem, if you sum up moments of areas about the neutral axis, this will be the equation. Area 1, Y1, plus, because there are two areas of concrete, area 2, Y2, that will be equal to area 3 or area of steel times Y3. Okay? So, to calculate that one, let me transfer the area 3 to the other side. Area 1, Y1, plus area 2, Y2, minus area 3, Y3, that will be equal to 0. Now, in Microsoft Excel, we can have a function which will look for the value of x as long as the value in one cell is 0. So let me encode that formula here. Area 1, Y1, plus area 2, Y2. No, I'm trying to reference the cells. Minus area 3, Y3. And it should be equal to 0. Right now, this is not 0 because we don't have our x yet. Let me shade this one for emphasis. So what we will do is use the goal seek function. In your calculator, you can also use the shift solve function. So data, what if analysis, goal seek, set this cell, this one, to a value 0 by changing this cell or the value of that cell. So when I press OK, Microsoft Excel is going to look for a value in X that will make this cell 0. Alright, so it was able to find X, and X is 5.65. Okay, so X now is 5.65. After solving for X, we can now solve for I. And I is the summation of IO plus AY squared of the individual areas. We have area for concrete and area for steel. So area 1 is concrete, area 2 is still concrete, and area 3 is steel. So let us now plug in the values here. So let me just copy, equals, referring to the cell, okay, so I'm trying to reference the table above, and IO is BH cubed over 12. Now IO is equal to BH cubed over 12. So we have equals B times H cubed over 12, and then drag it below. But for the steel, we don't calculate for the IO because we assume that the steel has 0 stiffness. Then for the area, that is base times height. Then for the area of steel, that will be NAS, or the modular ratio times the area. So that will be your area of steel. And for the Y, we were able to solve this one already here. So let's just refer to this table above. And then for the IO, that will be this value here plus A times Y quantity, or caret, then squared. Okay, so by dragging it down, we calculate for all the areas, concrete and steel. Then for the I, this is a summation, so let's use the summation function to sum the 3. Okay, sum the 3 values here above. So that will be 24,788. Alright, so here we already have our Y for concrete, which is the value of X, and Y for steel, which is X minus D. Okay, X minus D, or D, D minus X right here. And in this case, we are now ready to solve for the FC and the FS. FC is MC over I, or MY concrete over I, and FS is still MY of steel over I times the modular ratio. Don't forget that if you account for the stress in steel, you always include the modular ratio. So substituting the formula and plugging in the values, we can have this answer: 683.91 PSI. Okay, just remember that moment, which is 250 kip, should be multiplied by 12,000 to get a unit of PSI. Then here, N, which is 9, times M, which is 250, times Y of steel, which is 22.35 rather, divided by I, which is 24,788. So you will have that answer. Alright, thank you very much.